Travis.
And this is Jolene, and this is Beyond the Prompts.
In this episode, we're going beyond the prompt with AI and talking about the European Laboratory for Particle Physics. All right, let's get AI fired up. Jolene, what's our first question?
Well, really, I want to know how it all started. So let's just jump into what is baryogenesis?
Okay, so baryogenesis is the name for this big puzzle. Why there's more matter than antimatter? The Big Bang should have made equal amounts. Antimatter is basically a mirror of matter. Same mass, opposite charge. And when they meet, poof, they annihilate. So something tipped the scales. Probably some tiny difference in how they behave. We don't know what yet, but that's what the experiments are hunting for.
And where does quantum physics come into how that all happens and how it operates, like the software of it?
Good question. Quantum physics is the rule book. It tells particles how they can behave. Right after the Big Bang, everything was so hot and dense that quantum effects ruled everything. Now, baryogenesis basically asks, were there tiny quantum differences in how matter and antimatter decayed? Those little differences might have stacked the deck.
What is the Hadron Collider?
Think of it like a giant microscope. But instead of light, it smashes particles together at insane speeds. The Large Hadron Collider is this 27-kilometer ring underground at CERN, and it hurls protons near light speed and collides them. Those collisions briefly mimic the early universe, like right after the Big Bang, so we can see what pops out. That's how we test ideas about quantum rules, new particles, and the tiny imbalances that might explain why matter won.
Now, those smashing particles are happening all the time right now out in space, correct?
Yeah, constantly. Cosmic rays slam into our atmosphere all day, making natural particle collisions. The difference with the LHC is control. We know what we're colliding, and we can catch and measure everything that flies out. Nature's been running the experiment for forever. We're just trying to catch up and figure it out.
What are the Magnificent Seven experiments?
Let me double check. So, the Magnificent Seven usually means the 7 main particle experiments at the LHC. Each one has a different focus. Atlas and CMS hunt for new fundamental particles. Alice looks at quark, gluon plasma from heavy ion collisions. LHCb studies matter-antimatter differences. Totem and LHCf look at the Lansing collisions and cosmic ray lengths. And Moedal hunts for really exotic stuff like magnetic monopoles. Put together, they're like 7 camera angles on the same mystery: why the universe looks the way it does. The end game is to pin down the fundamental rules of nature: the building blocks, the forces, and the deep asymmetries. That's it. Find out what the universe is made of and why it works.
What purpose would that even do for our day-to-day life as human beings?
One moment. That's a fair question. 2 reasons. First, pure knowledge. Getting real answers to why is there something rather than nothing. That's a core human drive. Second, unforeseeable spin-offs. Historically, basic physics gave us semiconductors, GPS, and the web. Nobody promised that up front. The scientists aren't chasing a gadget. They're chasing understanding. The practical stuff tends to follow. Not guaranteed, but that's how progress has gone.
Where does the Zeptoverse come into this whole experimentation? And what is the Zeptoverse?
Right. So the Zeptoverse is the scale we're probing, meaning these mind-boggling tiny distances and times. Zeptoseconds are a trillionth of a billionth of a second. That's where these interactions live. So quantum rules set the behavior. The LHC smashes particles to probe that scale, and we chase tiny effects that might explain matter's edge. Think microscope dialed down to the tiniest gears of reality. The Zeptoverse is that workshop. It's where we hope the missing clues are hiding.
And what about known effects that CERN has, like on the human in life in our reality? Are there any known, I want to really say, side effects that is happening with these experiments?
One moment. So, there are no known harmful effects on people or reality, based on everything measured so far. Cosmic rays do similar collisions naturally. The real effects we do see are scientific insights and tech spin-offs. No evidence for portals, timeline shifts, or reality changes. Just careful measurements and a lot of data. We don't know what we don't know, and scientists are upfront about that. History says our tools have limits, and new instruments can reveal entirely new phenomena. That's actually why CERN exists, to push those limits.
What if the big bangs that we're creating now with CERN are creating universes just like we were created?
It's an imaginative leap, but right now there's no evidence for it. Some theoretical work plays with similar ideas, but nothing in the data points to CERN making new universes. It's a hypothesis people can explore, but today it's speculation, not an experimental result.
Is it possible that CERN is doing things and those things are being identified and recorded yet not released to the public? Just like in history, stuff has not been released to the public that could hurt the public. Is it possible that that's happening?
1 second. It's fair to ask. History does include real abuses and secrecy. As for CERN, there's no credible public evidence of hidden extraordinary effects. The collaborations are global, with results published and cross-checked. Could there be things we haven't found yet? Absolutely. But that's different from hidden discoveries. If solid, verifiable evidence emerged, that will change the scientific picture. Until then, the line between plausible unknowns and supported claims matters. Skepticism is healthy, but so is asking for evidence.
Nova, what is the CERN facility like?
Picture arriving just outside Geneva. On the surface, it feels like a university campus. Busy, multilingual, coffee everywhere. Then you realize 300 feet beneath you is a 17-mile ring. You walk past exhibits, then into cathedral-sized detector halls full of huge machines like Atlas or CMS, towering cylinders packed with sensors. The collisions are silent. Control rooms are walls of monitors, teams watching data streams, calm and focused. It's less sci-fi than people expect, more like precise global teamwork under fluorescent lights.
What is something about CERN that most people wouldn't know?
1 moment. One surprise is that CERN isn't just one machine. It's a whole campus of different accelerators and experiments. Another is the web was invented there. Tim Berners-Lee built it to help scientists share info. Also, the collider is colder than outer space when running, and the ring crosses under 2 countries. It's literally international underground. And most of the work is data analysis, not button pushing. Think of decays like clues at a crime scene. You rarely see the fleeting particle itself, but you see what it turns into. By measuring how often it decays certain ways or how long it lives, scientists test whether our equations are complete or whether something new is nudging them. Even tiny mismatches can hint at new particles or forces. So decays are like messages from nature. Most say, yep, the model still works. Occasionally, one whispers, something's missing. That's where discoveries live.
Explain what the Hadron Collider looks like. Is there 2 of them? Do they shoot at each other? What is going on here?
Give me a sec. Picture a single giant underground racetrack. One 17-mile ring. It's actually 2 beam pipes side by side. One beam goes clockwise, the other counterclockwise. Magnets steer them around at near light speed, and at 4 main points, the beams are nudged together to collide. So it's not two separate machines firing at each other. It's one ring with 2 counter-rotating beams that meet in specific detectors. And those head-on collisions are what the scientists study.
How did they build this thing? Where did it originate from?
Let me check. It goes back decades. After World War II, European countries wanted a shared science project for peaceful research. That became CERN in 1954. Over time, they built bigger accelerators. The LHC reused a 17-mile tunnel from an earlier machine. Building it meant lowering massive magnets and kilometers of cable down shafts, cooling them colder than space, and aligning everything with hair-thin precision. The first beam circulated in 2008. There were setbacks, like an early magnet failure, but it's really the result of decades of international collaboration, not a quick build.
When that magnet failure happened, what did it do?
Checking. It wasn't a physics event, it was an engineering accident. An electrical fault between 2 superconducting magnets caused a big energy release, boiling helium, damaging magnets, and shifting heavy components in the tunnel. No one was hurt, but it took about a year to repair and upgrade safety systems. So it was more of a power hardware failure, not anything exotic from the collisions.
What type of disaster could happen at CERN that would affect humans?
One moment. The real risks at CERN are industrial, not sci-fi. Things like electrical accidents, cryogenic helium leaks that can displace oxygen in confined areas, or radiation exposure for workers if protocols weren't followed. Those are serious, and that's why there are strict safety systems. The catastrophic scenarios people imagine, black holes or portals, have been studied and there's no evidence supporting them. The credible risks are local, engineering scale risks, and that's what safety teams focus on every day.
And those sci-fi risks, they're not a threat because we don't have the tools to determine whether or not they are a threat.
One sec. It's true that instruments have limits, but it's not just we haven't seen it. It's also that our theories and decades of experiments in natural cosmic ray collisions all line up. Outside that evidence is speculation. That's not proof either way. For now, the confidence comes from converging evidence, not from assuming perfect instruments.
What do all those past experiments align and point to?
Broadly, all those experiments line up with the standard model working extremely well. And at the same time, they show big gaps that still don't have answers.
And what's working well, and then let's go into what are the gaps where they're trying to find answers to fill.
Absolutely. Think of it as 2 columns, what's working and what's puzzling. Now, the standard model has passed an unbelievable number of tests. It predicts particles and forces with astonishing accuracy. The Higgs boson was predicted decades before it was found, and it showed up exactly as expected. That is a big win. But the gaps are huge. We don't know why matter dominates over antimatter. We still don't know what dark matter is, what dark energy is, or how to unify gravity with quantum mechanics. And there could be other particles or forces we haven't seen yet. It's like we've solved a beautiful center of the puzzle, but the edges are missing. And CERN is hunting for the first real clue that points beyond what we already know.
And what do they think, based on everything so far, it points to?
Checking. That is the big one. Based on what we've seen so far, many physicists think the standard model is incomplete. There's probably something else out there. New particles, maybe a faint extra force, or a deeper framework that unifies everything. The weird part is, so far, the standard model keeps passing tests. That's frustrating and exciting. It's like nature is teasing us. We're close, but not quite there. Most don't think we're at the end of the story. We just haven't found the next chapter yet.
I heard you say a Higgs boson experiment. What the heck is that?
Yeah, the Higgs boson is the particle linked to the Higgs field. Think of that field like a kind of molasses spread throughout the universe. Some particles slog through it and get mass. Some barely interact and stay light. The boson is the ripple, the little blip that proves the field is really there and that the mechanism works. Finding it didn't solve everything, but it nailed down a cornerstone of the model. That cornerstone is that particles get mass through the Higgs field. It's a central piece that makes the whole structure of the standard model hold together. Without it, the math falls apart. With it, everything is self-consistent. It doesn't answer every question, but it keeps the foundation solid.
So are you saying how matter is held together, how things are things, is what they're trying to figure out?
Kind of. We understand a lot about what makes stuff, like why protons and electrons have mass. But we don't yet know why the universe chose these rules, or why matter won out over antimatter. So the hunt now is for that deeper why, the next layer under the rules we already see.
If my wife and I wanted to take a trip to visit CERN, where's a good place to stay, and what airport are we flying into? And give us a little itinerary for a 3-day stay to visit CERN.
Can you even see
Checking.
CERN?
Yes, the visitor areas and exhibits are open. Fly into Geneva, it's the closest. Stay in central Geneva for restaurants and the lake, or near Marin for quick access. Day 1, settle in and explore the old town and lake. Day 2, CERN Science Gateway, plus any available tours. Get there early. Day 3 is flexible. Do a lake cruise, a quick Alps cable car, or museums before flying out. It's a memorable mix of science and Switzerland charm.
I guess we're doing a trip there.
What's a good restaurant to go to during that 3-day trip? Best restaurant? Any Michelin star restaurants?
If it's a once-in-a-lifetime meal, I'd do one Michelin-starred splurge night at L'Atelier Robuchon.
Well, I guess where they're keeping CERN at doesn't sound too bad. It sounds like a really neat little visit. I guess we'll put that on our bucket list. Until next time, stay curious and watch for more episodes from Beyond the Prompts.